Hi guys, good morning. Let's start. Almost everybody is there, right? Okay, so we'll start. Okay, so we were seeing gaseous state, right? So we have completed everything. I think we did. Did we do problems? Yeah, we did problems. Correct. So I think we touched upon everything, right? Ideal gas equation. Uh, this thing. What is that? Uh, Graham's law. No, no Graham's law problem. I think we have to do. Right. Just give me a moment. So problems on your way. Please check your groups. Right. So I have given you questions. So question numbers 5 and 6, marked it. Right. So we'll just look at the fifth question first. Right. So they are given 50 ml of H2 gas diffused through a small hole from a vessel in 20 minutes. So what they're asking is, what is the time taken for 40 ml of O2 gas to diffuse under similar conditions? Similar conditions means similar temperature and pressure and stuff, right? So what will be the time, right? Okay. So maybe I'll give you 2 minutes. Just think about it. So I told you how to calculate the rate of diffusions. So hope you remember the formulas, right?
Sir, from the next question onwards, can you send it like straight, sir? I can't rotate it in my laptop.
Oh, straight in the sense?
No, like it's aligned horizontally, sir.
Oh, that way you're telling. Okay, okay, understood, understood. Yeah, okay,
Yes, sir.
done. Yeah. Okay. So any answers? One second, guys. I'm thinking. Right. So let me help you solve this problem then. Right. So now, first thing what you have to do is calculate the rate of diffusion for H2 gas. Correct. Right. So now remember the rate of diffusion R will be equal to del V divided by del T, or it in terms of pressure it would be del P divided by del T. That is how much, like say initially I had 10 ml, and then say it became 5 ml, right? I'd say 2 minutes, and then you'll be able to calculate what is the rate of diffusion. Now they are telling 50 ml of H2 gas is diffused. So that del V is directly given to you. What is the change in volume is directly given to you. So if I take R of H2, right, R of H2 will be 50 divided by, what is the time? 20 minutes. Okay, so this would have been the rate for H2. Right. Okay. So now they're asking if I have rate for O2, similar conditions. Now in this case, I have 40 ml of O2. I don't know. I don't know the time. Right. This is what I have. Okay. Now these are the rates. Now we know how to compare the rates for two different gases. You have to use Graham's law of diffusion. Right. So if that's the case, I can easily tell that R of H2 divided by R of O2 will be equal to, can I say it will be root of m of O2 divided by m of H2. That's what your Graham's law says. R1 by R2 is equal to root of m2 by m1, inversely related to the root of mass. Right? Now that's it. You just have to substitute everything and get the answer, right? So if you do that, so maybe I'll make some space in the down itself. Right. So R of H2, R of H, okay, sorry. R of H2 by O2, correct? Okay.
Sir, is the answer 16 minutes?
16 minutes, let me check. Right. So R of H2 is 50 divided by 20 divided by 40. Divided by, I don't know what is the time, which is equal to, first mass of O2 should come. Mass of O2 is 32 divided by mass of H2 is 2. So this will be root of 16. Root of 16 is 4. That's it. Now you just have to do it. So I can write 40 by 20. I can just cancel the zeros. So I will be getting 5 by 2 is equal to 4. 4 into 40. 40. Oh my god, let me write it here, I guess that will be better. So 5 by 2 is equal to 4 into, very sorry guys, this is really happening. I don't know why this is happening. Either I don't know how to do use this stylus, or this stylus is very bad. Divided by t into 4. That's it. So now if you do it, this will go 2 times. Oh, sorry, I cannot do like that. Sorry. Right. So I think this will go 8 times. Right. So now t would be 8 into 4 is 32. 32 divided by 2. Yeah, 16 minutes. Yeah, that's the answer. Yeah, cool. Right. Yes. So now the next question, I think everybody understood this pure formula substitution. You just have to know how to calculate the rate for two different gases, and you should know how to compare the rates of the diffusion for two different gases using Graham's law. That's it. Right. Now, sixth question is a similar problem.
Sir, From your calculation, should it be?
Oh, it should be 64.
64, yes, sir.
Oh, wait. So it would be, if t goes here, 8 into 4 is
32 into 2, sir.
Oh, 32 into 2. Correct. Yeah, 64 minutes. It's absolutely true. 32 minutes. Yes. Okay. Right. So go to the next question. Right. So it's a similar, very, very similar question, except that something else is asked this time. So it takes 26 seconds for 10 ml of H2 gas to effuse through a porous membrane, right? So it takes 130 seconds for 10 ml of an unknown gas under identical conditions to effuse. So they're asking what is the molar mass of the gas. So this time everything else is, now last time everything else was given, the time was asked. This time everything is given, the molecular mass is asked for the unknown gas. Okay, so again, 2 times formulas. One for calculating rate, second comparing the rates.
Sir, is the answer 50?
50. Okay, I'll check. Yeah, 50 gram per mole. That's the answer. Correct. Okay, so do I need to solve this, people? Exactly similar thing. I don't think I have to solve it.
Sir, directly R1 by R2 is equal to root of M2 by M1. Sir.
Exactly. That's it. Yeah. And you have to calculate. So R1 in case of H2, it will be 26 by 10. For that gas R2, like of R of the gas will be 130 by 10. And that will be equal to root of the molecular mass of the gas divided by molecular mass of H2. That's it. Okay, right? Or anybody wants me to solve this question? Okay, I'll take it as a no. Fine, cool. So that's about this chapter, people. Okay, so yeah, we are done with gaseous state, right? So next chapter I told you we'll start would be atomic structure. Okay, fine. So we'll go with atomic structure. Right. So again, most of the things you might already know what we are going to study, what is there in this chapter, and all these things. So basically, we'll be seeing different theories, different atomic structure theories. The different scientists proposed different models of an atom, right? So we'll exclusively concentrate on the Bohr's theory, right? And then we will go for quantum mechanical theory. Quantum mechanical theory is going to see in terms of wave functions, right? And then the quantum numbers, all these things are a little important. Okay, so again, I'm not going to go into details that there are. So I can teach this chapter for I don't know for how many ever classes you want me to teach. That much information is there. But again, I'm just going to train you for the JEE point of view. So whatever the problems which are going to come, and obviously the conceptual questions, whatever is going to come, that you'll be able to answer. Okay, fine. So we know first. Okay, let me write that. What's the chapter name? Right. Okay. So we know that the first one was the first scientific person who spoke about the structure of atom or say anything about the atom was Dalton. Like that's what history says, right? But actually, even before Christ, right? Even before Christ was born, right? So there was an Indian philosopher. Okay, there was this Indian philosopher. I think his name was Kannad, Maharishi Kannad. Okay, so he was a Sanskrit philosopher. Okay, so he coined this term Paramanu, right? So we know, I think most of you are Tamil, right? I know Anu in Tamil means atoms, right? So what is this Paramanu? Paramanu means the entire world is made up of something small particles called as atoms. That's the term he coined. But again, we Indians, what is the problem with our Indians? Not now, at least before the civilizations even started, we had Indus Valley civilizations and stuff. But the thing is, we have everything in terms of observations and not proofs. Okay, so that is the reason why we don't see, even though like even before these people started building houses and these foreign people were hunting and eating, we had our own things and we were actually calculating where the stars will be at this particular point of time, and that how it affects our lives, right? So anyways, that like not going to the second part, but actually if you look at the panchangams, I don't know, like if you know what is a panchangam. It's a calendar where it tells you this is where at this particular point, at this particular day, Saturn will be at this position, Jupiter will be in this position, right? So all these were calculated and all these were perfectly right, right? But again, we don't have any proofs as such, right? There was no scientific proofs, any experiments like that were conducted, right? So that is why we actually don't see much credit given to us, but still we have our own things. Anyways, so he was the first guy to coin this term Paramanu, right? And then obviously there was other people like Aristotle, Democritus. All these people gave something related to atoms, but again, none of them had any scientific proof as such, right? But again, scientifically, the person who had any proof was Dalton, right? So we know what is Dalton's atomic theory states, right? So I think you have been studying it from your 7th or 8th class. So if I have to summarize whatever he said, every matter is made up of atoms, right? And atoms are the building blocks of matter, right? Atoms are indivisible, right? And if at all I'm going to have one type of element, that is going to have only that particular type of atom, in the sense that if I have sodium element, I'll have only sodium atoms in it, not like some other type of atom will be there. And each atom, right, each atom is going to have its own constant mass, right? And then say that during a chemical reaction, the atoms undergo some kind of rearrangement. So yeah, these are all the points given by Dalton, and obviously we know which are the points which are wrong, because after that particular theory got evolved, right, other scientists who came after that, say your Thomas, what is his name, cathode ray experiment, what is his name, guy, what is the name of the guy? Okay.
JJ Thompson, sir.
Thank you so much. Yes, JJ Thomson, right? So JJ Thomson, who conducted the cathode ray experiment, he proved that yes, atoms are divisible. They have something called as electrons. Okay. Then again, we will see that the cathode ray experiment now. Anyways, I'm just giving you the overall picture. And then came Millikan. Millikan was able to tell about the charge of electron, charge or mass. Okay, I think it's charge. Okay, fine. So charge or mass. Anyways, E by M ratio was coined by Thomson, right? So then came Millikan, then came Goldstein. Goldstein discovered protons, and then I had Chadwick. Chadwick discovered neutrons, right? And actually before that there was Rutherford. Rutherford discovered nucleus, right? So eventually Dalton's theory faded away, right? So because all of these guys proved that atoms are divisible, inside that atoms we have so many other things. Now we have so many other stuff. I have something called as mesons, positrons, all these stuff are again there, but again for our levels it's not required, right? And then again the Thomson's thing was actually predominantly used until Bohr gave his model. Okay, so I will see what Bohr told. Right, again, Bohr had his own, Bohr's theory had its own limitations, right? Then came the quantum mechanical theory, right? So quantum mechanical theory, now we till now use only quantum mechanical theory, right? So unless and until some other scientist gives another theory, we are still going to follow this only. Okay, fine. And then we'll see everything in little in detail. Okay, fine. So first we'll start with, one second, guys, one second. Yeah, so we'll start with Thomson. Okay, so we'll see what he did, okay, how he conducted the cathode ray experiment and how he found out the existence of electrons. Okay, fine. So I'm just going to give you the experimental setup. Okay, so there was I say this is a tube made up of glass. Okay, and there was two openings, okay, into this. First opening was for giving H2 gas, okay. The other is for a vacuum pump, okay. And obviously I'm going to fit two electrodes, and I'm going to supply a very huge voltage, a very high power supply, high voltage power supply, okay. And obviously in this region I'm going to have the H2 gas present, okay. Right, fine. And one more thing I had, okay, now, okay, one second. I should be doing it a little differently. Okay, let me connect the negative terminal here, positive, negative, positive. Okay, now that would be better, right? So obviously, you know, the negative terminal is what is my cathode, right? Positive terminal is my anode. Okay, right. So now, when he switched on the battery, right? When he switched on the battery, when this power supply was done, and obviously you should maintain very, 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 very low pressures for this like basically he tried with very high pressures, and then it was nothing was happening, and then he kept on reducing the pressure. Now at a pressure was around 10 power minus 6 atm or something like that, right? Then he saw something happening, okay. And there was one more thing here. So this particular anode, you see, there are going to be holes in this, okay. This is what is called as perforated anode, right? When I say perforated means this is going to have some holes into this, okay. Now this particular area what I have here, right, now this is coated with a ZNS paste, okay. ZNS is this is going to provide a screen, okay. Let me tell you what is that used for, okay. Anyways, now when he switched on the battery, right, when he switched on the battery, there are few as he observed something. What did he observe is that he saw something moving from cathode towards the anode. That's what he saw, right? He just saw something moving from the cathode towards anode. And how did he confirm it? Is when something is going to hit this ZNS screen, right, I'm going to have some bright spots on this, right? Those are what are called as scintillations. Okay, those are what are called as scintillation. Scintillation is nothing but bright spots. Okay, so again I repeat, so he saw something moving from the cathode towards the anode, and it was proved with the help of scintillations on the ZNS screen. Okay, then fine. So he didn't know exactly, he literally had no clue what is happening. Okay, so then he wanted to find what exactly are these, what are these made up of, is are they charged, are they uncharged, if they are charged, positive or negative, or if it's a particle. He just wanted to know everything. Okay, fine. Okay, now since he said that something was moving, just give me a moment. Sorry guys, it was an important call I had to pick. Okay, so where was I? So yeah, so he saw something moving from cathode to anode, so he just named whatever these are to be cathode rays, right? Because it's starting from cathode, it's moving towards anode. He called them as cathode rays. Okay, fine. Then he wanted to find what are the properties of these so-called cathode rays. Okay, so what he did is, let me make a rough diagram so that you'll understand. So what he did, if everything is going to be same, assume that these are the cathode rays. Okay, these are the cathode rays. Now what he did is he applied electric field. He applied one more electric field, say another. Okay, these are the electrode plates. Okay, now obviously I need to have uh, power supply, right? So wait 1 second. Right, so power supply, I should put say this is negative, right? Negative, positive, negative, positive. Okay, now this was happening. So basically you see this is positively charged, this is negatively charged plate. Okay, so when this was not there, when this no external electric field was applied, what he found out that these cathode rays are going to move in straight lines. Okay, these cathode rays without any deviation, they just moved in straight lines and hit the ZNS screen. Okay, but when this was applied, right, when this external electric field was applied, what he found is these cathode rays are bending towards the positively charged electrode. Okay, he found that the cathode rays are deflecting towards the positive electrode. Okay, that obviously means it can mean only one thing. Obviously what it means is that these cathode rays are negatively charged. Okay, these are negatively charged. Obviously that can be the only reason this is happening, isn't it? Okay, fine. Now then he understood. Okay, then what he wanted to see, okay, this is a negatively charged, still now it's just a ray. Okay, we don't know whether it's going to be a wave or a particle. So then what he did is, again I'm just going to give you a rough diagram. Okay, now assume that these are the cathode rays. Okay, so what he did is he placed a paddle kind of stuff. Okay, so basically when it's like it can rotate, right? You can think it of a frisbee, if you have played with a frisbee. Okay, so what is going to happen if if something of some mass or some energy is applied to this is going to rotate. That we all know, right? So what happened is if he placed this rotating wheel in the path of these cathode rays, right? What he saw was this was rotating. Okay, this was rotating, right? Now please understand, this time, until this time, if some, so obviously this means this has some energy. That's what you need to understand. Okay, this has some energy. Obviously only then this will be able to impart that energy, and that can be translated into kinetic energy of this rotational motion. Right. Okay. Now, please understand. Until this time, it was going to happen in some 1800s. I don't exactly remember the year. What you have to understand is until then, only equation concerning energy was this Einstein's equation: E is equal to mc square. Okay. So what you have to understand is something which has mass, right? Only those stuffs can have energy. That's what it means. Okay. Something which has mass, only those things will be able to have some energy. Right now, obviously you can ask me, sir, what happened to E is equal to h nu? We are going to come to that, but till now we are talking about the history. Until this point, Planck's equation didn't even come into the picture. We will speak about it when it came. Okay, so now what you have to understand is obviously this cannot be a wave, right? I cannot tell 1 kg of sine wave, half a kg of cos wave. It's not going to be like that, right? So obviously this cathode rays are going to be made up of particles, right? And obviously these particles are negatively charged. Okay, and he gave them a name, right? Negatively charged particles, and that is where your electrons came into the picture, right? So he concluded that this is definitely going to be because of a negatively charged particle. Everything according to his experiments, all these observations, this is what he saw, and he gave he said that these cathode rays are made up of negatively charged particles called electrons. Okay, now you will be wondering where the electrons came from, right? In the cathode ray, you just put hydrogen. So now we have a proper explanation, but at that time he was not able to give. But now I'll be able to give you a proper explanation. Please understand, when H2 is there, right, and a very high electric field is applied, you will be getting H plus an electron, right? Like this dissociation is going to happen when I'm going to supply a huge amount of electricity. Okay, so you see that electron is coming. Obviously, that is the reason for all this happening. Okay, right. So based on all or any questions, people, from this? Okay, fine, cool. So now he discovered electrons. Now he has to fit in the electrons inside the atom somehow, right? So that is where you have your Thomson's atomic model, right? So you have Thomson's atomic model. Okay, right, fine. So now he discovered electrons, but and one more thing I forgot to tell you, before seeing the atomic model, people, he did one more thing. Okay, so what he did, that I'll tell you. Sorry. So what he did is, I have the cathode rays. Okay, right, I have the cathode rays with me, right? So what he did is, he applied electric field and magnetic field perpendicularly. Okay, he applied electric field and magnetic field. I'll tell you how exactly he did it. Okay, so basically when he applied the electric field, obviously I'm going to have some kind of deviation. Okay, say it is going to hit a point X, right? Now he applied magnetic field, and then he is going to bring back to its original position if it was going in a straight line. Okay, and based on this, he was able to calculate the charge to mass ratio of electrons. Okay, he was able to calculate what is the charge to mass ratio of these electrons, and it's correct. Okay, I don't remember the exact value, but that is not important for you. Also, you don't have to remember the value, but you have to understand how he was able to find the charge to mass ratio. Then again, there is a derivation for this. Okay, I like you, if you're interested, please go through the derivation. Okay, it's a pretty simple derivation. You just have to make sure that the force due to electric field and the force due to magnetic field are going to get balanced, right? And obviously the electric field, you will have the charge coming, right? And you will be able to get that out. Okay, anyways, so this is what the point which I missed. Anyways, now we'll go to the Thomson's atomic model. How he did it, I think you all know. It's called plum pudding model or watermelon model, right? All these things. So he said that the atom is a sphere, right? Atom is a sphere of positive charge. This entire thing is a positive charge, right? So then what he said is, electrons are embedded here and there like this, right? So that's what he said, as simple as that. Okay, so atom is a sphere of positive charge and electrons are embedded inside the sphere of positive charge. So that's why it's called watermelon model. Say the fruity part, the red part, is what is my positive charge, and electrons are the seeds. You can just compare it like that. So that's why it's called as watermelon model, right? Okay, fine. Okay, so what are the problems with this, right? Now, as such, when he discovered this, there was no problem, because he was able to prove that atoms are neutral, right? They are not charged and stuff, because the amount of positive charge and the amount of negative charge is okay, right? And he was able to find what is the charge to mass ratio. As such, there were no problems. Now the problem came when other scientists found out other discoveries, in the sense that when they discovered protons, when they discovered nucleus, all these things, then his model became a problem, right? Okay, so that's about Thomson's atomic model, right? Then came your Rutherford, right? So let me tell you one thing. Okay, I'm going to tell you a small story, right? So your Thomson was awarded the Nobel Prize in physics, not in chemistry. Okay, so the Thomson was awarded the Nobel Prize in physics for discovery of electrons. Okay, so what happened is, Rutherford was a student, right? Rutherford was Thomson's student, and then it's like the student disproved the teacher's own theory, right? And then came Niels Bohr. Bohr was a student of Rutherford. Okay, Bohr was a student of Rutherford. Again, you see that the student is actually disproving the teacher's theory. Right? It's a small story. It's like, obviously you have to know this, right? Just to make sure that someday I expect you to get better than me. That's what I'm implying by this. Okay. So anyways, so Rutherford came, right? So we know what experiment he conducted. Can you tell me what is the name of the experiment?
Alpha ray scattering
Yeah,
experiment.
right. So it's called alpha ray scattering experiment. Okay. So I'll just quickly get you through that. Right. I'm going to have a very thin gold foil made of 100 atom stick. Okay. Very thin gold foil. Okay. Then he had alpha rays. He made alpha rays to bombard to this gold foil. And we know what are alpha rays. Can you tell me what are alpha rays? What are they made up of?
Helium 2 plus.
Ah, correct. Right. They are made up of doubly charged helium 2 plus. Right. Okay. So then he had three observations. Now, based on these three observations, he made three conclusions. I'm not going to write anything. I'm just going to tell you what happened. So, first observation is he found 90, most of the rays just passed through the gold foil. Again, he was able to prove it with the help of ZNS screen here. Right. He was able to prove it with the help of a ZNS screen here. Again, scintillations were formed beyond this. Okay. Then he found out that some of the rays, right, some of the rays got deflected by an angle of theta, right. And then what he found out was one in some millions of rays, one in thousand rays just retraced their path. That means the angle of deflection was 180 degrees. Okay, so these three were the observations. Most of the rays passed through, some of the rays got deflected by an angle of theta, some more, and 1 in 1,000 rays or 1 in million rays got deflected by an angle of 180 degree, or they retraced their path. Right. Okay. Then based on these three observations, he gave three conclusions. First observation, most of the rays passing through the gold foil. He said that most of the space inside the atom is empty, right? And he said that some of the rays are deflecting an angle of theta. That will happen only because of repulsion, obviously, because there should be some positive charge inside, right? Oh, actually, uh, before this, right, before Rutherford, actually there was Goldstein who found out protons. Okay, now assume that protons were discovered. I'll tell you how protons were discovered, but for now, assume that the protons were discovered. Okay, fine. So he says, since there is a deflection happening, this deflection will happen because of what is that? Hmm, because of presence of protons, because they are also positively charged. Okay, fine. Then coming to the third observation, he said, the rays are retracing their path, and that will happen only because when I'm going to have a very, 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 very strong positive charge, and obviously that was coined to be your nucleus. Okay, right? So this is how nucleus was found out, right? So again, he has to fit in everything, right? He has to fit in electrons, he has to fit in protons, he has to fit in nucleus, right? So everything he has to this thing. So he said that most of the mass and most of the positive charge is in the nucleus. Okay, most of the mass of the atom and most of the positive charge of them is embedded in the nucleus. So basically electrons are somewhere inside the nucleus, or say very, very close to it, or not electrons, sorry, protons. Okay, protons are very, very close to the nucleus, or some, I would say, like, he didn't give a clear cut clarification of what is that, right? But he said that protons and nucleus are going to be very, very close to each other, right? Okay, so I would say this is the nucleus. I mean, I didn't say, he said that this is the nucleus, most of the space along with protons are here, right? And then he said that the electrons are going to be continuously revolving around the nucleus like this. Okay, electrons here, obviously electrons were already found out, so he said that the electrons are going to be continuously revolving around the nucleus, right? Okay, now we know what are all the problems here. If electrons are going to continuously revolve, if we are going to continuously run around the ground, obviously we'll lose our energy and we'll fall down, we'll fail, right? Same goes with electrons. If it is going to move, that too these are positively charged and electrons are negatively charged, this electrons has to move against the force of attraction of the nucleus, right? So obviously they will drain their energy in a matter of like femtoseconds, 10 to the power minus 12 seconds. Like, again, I'm giving you a rough value, right? So like very short span of time, they're going to lose the energy, and obviously these electrons are going to fall into the nucleus, right? So the entire stability of the atom was a very, very big question here, right? And one more problem, one more demerit of this is that, hope you understand, there is something called as a spectrum, right? So basically, a spectrum is a collection of wavelengths, again, collection of wavelengths and frequencies. It's like when I say spectrometer or spectrometry, basically I am going to have a scale which is going to have some 0 to lambda. All these things are going to have be graduated, right? This is what is called a spectrometer or spectrum. This is what is called as a spectrum, right? So in the spectrum, I know what all we are going to have. We are going to have say gamma rays, x-rays, microwaves, radio waves, UV light, visible light, IR region. So many things are there in this, right? Obviously all of them are going to have different wavelengths, right? So fine. So anyways, like what happens is, since you see that the electrons are continuously revolving around the nucleus, right, now it is going to give a variety of values of energy, in the sense that, say, some entire region like this would have been the energy value given out by the movement of electrons, right? So these are what are called as continuous spectrum, right? So you see, it's not like a single value. You see that obviously a bulk, so many values are embedded into this, right? So this is what is called as continuous spectrum, right? So according to his model, I should be getting a continuous spectrum, but when other scientists performed the spectrum, they got a line spectrum, say something like this, only one particular line, okay, one particular wavelength. That's what I'm trying to say. Okay, so you see that this is a line spectrum, but what according to him, I should be getting a continuous spectrum, right? So again, that was a problem. Stability was a problem, spectrum was a problem. Okay, so again, to overcome all this, we have to go for another theory, and I have to tell you how Goldstein discovered protons, right? So Goldstein discovered proton. He just copied the experiment. I would say, I should not say scientist copied the experiment. He just took the idea from Thomson. Okay, so the only difference he made this time is, okay, same things, everything is same, right? Now, what he did last time, I had holes this side and I had a ZNS screen this side, correct? Right, now this time what Goldstein did is, okay, this time what Goldstein did is he made the holes this side, that is in the cathode side. Obviously, you see this is the negative charge, positive charge. Okay, so obviously hydrogen gas, everything is there, no issues, right? So he found out, now instead of making a hole here, he made the hole on the cathode side, right? Obviously the ZNS screen is placed now this side. Okay, now this is what is called as your perforated cathode. Last time it was perforated anode, this time I'm going to use perforated cathode. Okay, so now what he found out is, this side also he was able to see scintillations. Okay, so he considered that something was moving from the anode towards the cathode. So those are what are called as anode rays, right? So obviously, so this, again, all the other things matched whatever Thomson did. He also conducted he put an external electric field, external magnetic field, everything was done. But the only difference is that the direction was reversed. Instead of moving from cathode to anode, the rays were moving from anode to cathode, though that's why they are called anode rays. And he concluded that they are made of positive charges, and he called them as protons. That's it. This is how protons were discovered. Okay, right, fine. So that's about, we saw three things, right? We saw about nucleus, protons, and electrons, right? So one more thing is about your neutrons. So neutrons were given by Chadwick. I mean, not given by Chadwick, he discovered neutrons. Okay, so it was pretty, this thing, he had some I think it's not sure what was the element. It was boron, or I'm not sure. Okay, so anyways, he found it through, he actually found it through accidentally. Okay, he found this, he discovered protons through an accident. He was trying to do something else, right? But he had a radioactive element with him. I just tell you though, like, I'm not exactly remember what is the element he was using, right? So what happened is, he was actually using a radioactive isotope of an element. Okay, so that radioactive isotope it decayed, right? So he saw that some neutral thing was coming, right? It was not charged, it was nothing, it had a mass similar to the protons, but this was not charged. Okay, so then he concluded that it is going to be called as neutrons because it is neutral. Okay, now if you're interested, please go through what was the element, right, and how it decayed, right? So, but again, that was the overall thing which you have to know. There was a radioactive isotope that started decaying. In that decay process, he found out that something neutral was coming out with a similar mass similar to that of protons, right? And then he concluded that these are going to be called as neutrons. That's it. Okay, right. So we now figured out all the subatomic particles: electrons, protons, nucleus, and neutrons. Right. Okay. Now, obviously, you saw. Okay, even though these were discovered, right, putting them into an atom, how these things are arranged was still a question, because nobody was able to give a proper answer. Okay, right. Now this time before we go on to see the next theory, there was an evolution in science, right? That evolution was science was my Planck's quantum theory. Okay, so again, I can speak about this for another 2 days, but I'm going to give it to you in a nutshell. What exactly is this, right? So till now, people, like, till Planck gave his theory, it was all Newton. Newton was the dawn of science. Okay, right? Newton was the dawn of science. It's called Newtonian physics or classical physics. Okay, so there were a lot of he did a lot of research. It's not only your motion stuff, which he worked on black bodies. He worked on so many stuff, right? So okay, so why am I talking about this? Is because Newton obviously spoke about the motions, isn't it? So this motions, the equations of motion which he gave, were not applicable for the movements of electrons. Okay, we know that electrons are obviously moving inside the nucleus, right? That Newtonian the equations of motion were not able to correctly predict what is that correctly predict the motions of the electrons inside the atom. Okay, and then one more problem is his work on black body, right? We know what is a black body, right? A black body is one which is going to absorb or which is capable of releasing any amount of energy. Right, whatever energy you give, it is going to take, and it is capable of releasing all the energies also. That is what is an ideal black body, obviously, right? Ideal black body should be able to take up everything and release everything. That is ideal, but obviously we don't have any ideal black bodies as such. Okay, so again, Newton predicted that it is going to have a continuous spectrum of absorption, right? Whatever energy you give, say it is not going to dip, it is not really going to matter. It is just going to happen. It's just going to take up whatever the energies you're going to give it, irrespective of whatever the values you have, right? But Planck had a different idea. He was really he was not agreeing to whatever Newton was saying, right? So he came up with his own theory called Planck's quantum theory. It was basically developed for black bodies, but then Planck applied it for even in the case of atomic structures. Atomic in the sense how electrons and all these are gonna interact with each other. Okay, so fine. So what Planck said is, black bodies are not, yeah, they are capable of absorbing values of energy, but not like 0 to infinity, right? So there is going to be a particular value, right? Say some value A, right? Now if this is the smallest value which the black body can take, if I'm just telling again, repeating, if this is the smallest value of energy, the smallest value of energy which a black body can take, then I can have energies absorbed or released only on this kind of values. N is an integer. Okay, now I cannot have 0.5 a value coming out or 0.5 a energy absorbed. It's not possible. Now what is a is the smallest energy which can be absorbed or released by the black body. Okay, so this a is the smallest value. Now based on this value only, all the other values which can be absorbed or which can be released which can be taken up by the black body. Okay, so it should be the energy released or energy released or energy released should be integral multiple of the smallest value. That's what he said. Okay, and this smallest value, he just called it quanta. Right, the smallest value of energy, he called it as quanta. Quanta means one packet. Okay, one packet of energy. Okay, so obviously, if at all you're gonna go to a say a shop and you're gonna buy water packets, right? You cannot buy 1.5 water packets. You can buy 3 water packets, 4 water packets, but you cannot buy anything in fractions. Same thing. Whatever the energy you have, it is gonna come in packets, right? So obviously, all the energy values which are accepted can only be integral multiples of this particular value called the quantum. Okay, now how he applied it to atomic structure, let me tell you that. So what he told is atoms are made up of all atoms are made up of numerous number of elementary oscillators, right? All atoms are made up of something. All atoms are made up of elementary oscillators. And then actually his research was going on, he was working on this, and by in the same simultaneous time, the electrons were discovered. Okay, then he told that these elementary oscillators are nothing but electrons. Okay, so inside an atom I'm going to have so many things, so many this elementary oscillators which will be oscillating like this, like this, like this. They're going to be oscillating. Okay, right. Now what he said is the energy of these oscillations, the energy of these oscillators, energy of these electrons, or energy of these elementary oscillators. What he said is proportional to the frequency at which the oscillations are happening, right? Or what is frequency? Number of cycles per second, right? One cycle, or say in a per second, how many cycles can happen? That is what is your frequency, right? So he said that the energy of these elementary oscillators or these electrons are going to be directly proportional to the frequencies in which they're going to vibrate or they're going to be oscillating, right? So then obviously to remove the proportionality sign, I have E is equal to h nu, where this h is what is called as your Planck's constant. So this is how E is equal to h nu came into the picture. Okay, and I know what is this value. It is going to be approximately, h value is 6.6. Again started. (6.6) into 10 to the power minus 34, right? You can, if at all you want the units, it's pretty simple. Energy is joules, right? This is per second, so you can easily say it is going to be joules per second. That's it. Okay, that will be the unit of Planck's constant, which is 6.6 into 10 to the power minus 34. This is 34. Okay, so that is about your Planck's theory. So based on Planck's theory only, what is the time? Okay, we still have half an hour. So based on Planck's theory only, your Bohr gave his own atomic theory. Okay, so we'll see how it happens. Right. Okay, so now we are going for Bohr's atomic model or Bohr's atomic theory. Guys, if you have any questions, you can always stop me right there and ask. If is there any questions you want to ask? Okay, fine. I hope everybody is following. Right. Okay, fine. So Bohr's atomic model, we'll see what are the first postulates he said. First thing he said is this. Okay, first of all, the electron has to be given a place, right? So he said that electrons are going to be there in something called as stationary orbits, right? So electrons are situated, or they're going to revolve around the nucleus, not like randomly. You cannot have any position or anything random positions for the electrons. They are going to be in their own homes called their stationary orbits. Every electron, each and every electron has its own home. It's not like all the electrons will have same homes, right? Every electron has its own stationary orbit. Right. Now, what is the speciality of the stationary orbit is as long as the electron stays in its own stationary orbit, there is no energy released, there is no energy absorbed also. Okay, as, oh, no. Yeah, so as, not energy released is okay, energy absorbed can happen, sorry. Okay, so like what he said is, as long as the electron stays in their own stationary orbits, obviously it can shift to other stationary orbits, right? As long as it's going to stay in its own stationary orbit, the electrons are not going to release any energy, or the energy of electron is not going to get consumed because of their rotations in the stationary orbits. That is the speciality of these stationary orbits. Now I have overcome the problem with Rutherford, isn't it? Because Rutherford didn't give me the exact position of electrons, right? So obviously the electrons were dissipating energy and eventually they fall into the nucleus, but that problem is exactly sorted here, right? Okay, now if you want to shift the electron to not its own stationary orbit but to higher stationary orbit, obviously in that case you have to supply energy. Okay, and then what he said, yeah, he said that these stationary orbits are circular, but again we actually have a different theory now. The orbitals are going to be actually elliptical in nature. Anyways, we'll see about it later. So he said that these things are going to be circular. Okay, and one more thing is most important point, the energy of this stationary orbits are quantized. So that's what I told you. He took the idea from Planck. So what do you mean by quantized? Obviously, there is going to be one small value. Based on that small value only, all the other stationary orbits energy values are going to be available. Okay, so the energy of stationary orbits are quantized, or in other words, I can say that energy of electrons in different stationary orbits are also going to be quantized. Okay, right, fine. So these are all the different points told by your Neil Bohr. Okay, fine. So then again, there are a lot of derivations. He found out so many things. He found out the energy of electron in the nth orbit, or say that this is the energy of the nth stationary orbit, right? So he found out the radius using mathematical calculation. See, his theory is not, it is not experimental at all. It is purely theoretical. Okay, based on mathematical calculations, theoretically he calculated all these things. Okay, so he found out what is the radius of radius of the stationary orbit, nth stationary orbit, right? He found out what is the velocity of an electron in the nth stationary orbit. Okay, so and he also found out something called as ionization energy. Okay, I'll tell you what is ionization energy, not the ionization energy which you know now. Okay, so anyways, so he found out the ionization energy, and then he was even able to find what is the transition energy, in the sense that if I have to shift electron from one stationary orbit to another stationary orbit, how much energy you have to supply, or how much energy will be released if the electron comes from higher orbit to lower orbit. All these things he calculated. Okay, and there are derivations for all this, but we again are not going to see any of the derivations. I am directly going to give you the formulas, right? So starting with En, right? So or I'll start with radius. So radius Rn is equal to 0.0529 n square, or n. That's why. That is why. 1 second, guys. Let me come back. Okay. Right. So it's um, yeah, 0.0529 n squared by z nanometers. Please be very careful. Okay, this is very important. You will see different formulas. 0.529 you will see in terms of angstrom units. If you just remember anything, just remember any one of it, right? Different units are going to come depending on what decimal places you're going to put here, right? So this thing is Rn, the radius of the nth orbit is equal to 0.0529 n squared. N is the stationary orbit number, right? And Z is the atomic number. Right, Z is the atomic number. So that's the formula for radius. Okay, next velocity of electron in the nth orbit would be 2.18 into 10 to the power 6, correct? Yeah, 10 to the power 6 Z divided by N. Okay, so again you see Z is the atomic number, N is the stationary orbit number. This is 2.18, right? Okay, so that is the velocity. And let me give you the energy, En. Okay, so next is energy of the electron in the nth orbit or nth stationary orbit. Okay, so that is minus kz squared by n squared. I'll tell you what is this k. Now this k is going to depend on what unit you want the answer to be in. Okay, so if at all you want the answer to be in terms of electron volts, that would be 13.6 k value I'm talking about. If you want the electrons in terms, sorry, if you want the En value in terms of electron volts, then you'll put k value as 13.6. If you want the answer in terms of joules, then you have to put the k value as 2.18, right? 2. Right, 2.18 into 10 to the power minus 18. Okay, so if you want the answer in terms of joules, you are going to put the k value as this. Okay, 2.18 into 10 to the power minus 18. Okay, you have to remember these values, guys. There is no other way. For this chapter is again full of formulas. Okay, so if you remember the formula, you are set, right? Okay, so we talk about Vn, Rn, and En. Then we'll speak about the transition energy. Delta E is what is my transition energy. If at all an electron shifts from one orbit to another orbit, right? So what is it going to be, right? So always remember, it is always going to be E final minus E initial. That is where it is going, the electron, where is it going, and EI is where the electron is coming from. Right. So anyways, if we just put these formulas, right, I can take k z squared common, only n is going to vary. Is it not? Depending on the depending on where the electron is coming from and where the electron is going. Right. So that would be easily, I can say, so delta E will be equal to EF minus EI, and that would be k z squared into 1 by Ni squared minus 1 by Nf squared. Right, so Ni is the initially where the electron was present, and Nf is the finally wherever the stationary orbit the electron is present. Okay, so this is your transition energy. Okay, now at last, coming to ionization energy, right? I have to give you the definition first because it is not the definition which you know now. Okay. Right. So what is the definition of ionization energy he gave, or say what was perceived at that particular point of time, is it is the energy required. Okay. It is the energy required to take the electron from initial orbit, that is first orbit, okay, to infinity. Very simple. Right. When I'm going to take the electron from the first orbit to the infinite orbit. Okay, electron from the first orbit to the infinite orbit. What is the energy required? That is what is called as your ionization energy. Now I'll be able to use this formula itself, delta E formula itself, put n1 is equal to 1 and nf is equal to infinity, so you will see that this term will become 0, this term will just be 1. So you can easily calculate what will be the ionization energy. It is just gonna be kz square, right? So remember, this is not going to depend on where the electron is present, right? The electron has to be present only in the first orbit. It's now, you know, hope you understand now what is the difference between the ionization definition we have now and the ionization energy definition they gave. Now what is the definition we have? It's the energy required to take out the electrons in the valence shell. It's not the first orbit, right? But here it's going to be from the first orbit to the infinite orbit. Okay, so you can easily get the formula as kz squared. Okay, fine. So that's about different value with different terms you found out. Okay, fine. Now, what is the time? Okay, we have time. So the next thing what you have to understand is we have to look at the emission spectrum of hydrogen. Actually, that's about the Bohr's theory. Okay, that's about the Bohr's theory. But there is a little continuation of Bohr's theory, which other scientists just continued with this work, right? So we are going to see emission spectrum of hydrogen. Okay, so hope you understand what do you mean by emission. Emission only will happen if I'm going to come from higher orbit to lower orbit, right? Okay, so now if you look into it, right, so I am going to give you, so you can just directly derive it from delta E itself. Now delta E is equal to you see that was kz squared into 1 by ni squared into 1 by this thing. Now this delta E will also be equal to hc by lambda. Hope you know. Okay, first I'll give you the formula. Z is equal to h nu, and I also have a formula like hc by lambda. I think these are some preliminary equations, you should know it. Okay, so this hc by lambda, right, was equal to k z squared into 1 by n1 squared minus 1 by n2 squared. Right, now remember, in this case this n2 is the higher orbit, right, and this n1 is the lower orbit. Okay, that is how you must consider it. Okay, but if you do it, I'm going to get a negative value. Okay, but you don't have to worry about it. Just remember that n1 is the lower orbit and n2 is the higher orbit. Okay, fine. Now I want the answer in terms of, so this is in terms of energy, isn't it? But if I have to record the spectrum, right, obviously, you know, I told you in spectrum it is going to be in terms of either frequencies or it is going to be in terms of wavelengths, or I have something called as wave number. Okay, so this wave number nu bar, right, nu bar is what is called as your wave number. This is nothing but 1 by lambda. Okay, so this 1 by lambda, so if I have to calculate 1 by lambda, what you have to do, this hc has to go here. That's the only thing you have to do, right? Okay, so if you do that, right, so 1 by lambda will be equal to, I'm going to directly give you the equation, will be RH. Okay, this is going to be another constant, because you see there is already a constant k, h and c are another constants. Now that all two will bring together to bring this particular guy, that is your Rydberg's constant. I'll tell you what is the value, don't worry. So anyways, this is RH, right, into RHZ squared, obviously. RH z squared into 1 by n1 squared minus 1 by n2 squared. As simple as that. Right? Okay, now what is the value of RH? RH is what is called as your Rydberg's constant. Rydberg's constant value, let me give you, where are you? I think it's some 1.09 into 10 to the power 1 second, guys. Yeah, got it. So it's 1.09 into 10 to the power 7 per meter. That's the value for RH. Okay, RH is Rydberg's constant. right? So fine. So why did I tell you all this? Is because depending on what is the wavelength or wave number given by a particular transition, right? Different scientists worked on different areas of this. Okay, so among this, let me tell you the names. I think you know what I'm going to speak about, but still. So I have something. I have first scientist was Lyman. Next was Balmer. Then can you continue? Lyman, Balmer. Then
Passion.
yeah, Passion. Then
Bracket.
yeah, Bracket. Then
P fund.
yeah, it's not P fund. It's just fund. P is silent. Okay, so Bracket and Fund. Okay, I have one more. I have something called as Humphrey, but again, that is not required for you. But again, you can just know, right? Humphrey. There should be H. Okay, so anyways, so these people are actually going to work on different areas or different transitions which are going to happen between the stationary orbits. Okay, now pretty simple, guys. It's like remember, you are just going to look into this value, right? So from a higher orbit to which lower orbit the electron is going, that's what is more important, right? Now, please understand for Lyman, right, the n1 value where the electron should come should be in the first orbit, should come to the first orbit. For Brackets, actually, then wait, let me give you certain things, right? So what is that? N1 is equal to 1. Obviously, I am going to have different wavelengths produced. So for remember, for Lyman, the spectrometer is going to show somewhere in the UV region, okay, ultraviolet region. And for Brackets, oh wait, Lyman Balmer series next, right? For Balmer series, right, N1 is obviously going to be 2, right? And this is going to come in the visible region, visible light. Okay, then comes Lyman Balmer Bracket, right? For him, N1 is 3, and it is going to come in IR, infrared. Okay, and did I miss anything? Oh, it should be Lyman Balmer Passion first. I'm really sorry, guys. This is not Bracket. This is Passion. Right, then comes Bracket, right? So there N1 was 4. Again, it is going to be in IR only. And at last comes your Fund. For him, N1 will be obviously 5. And here also it's IR. Okay, right? Fine. So these are all, obviously you just have to put the formulas, right? And the only thing which is going to change is the N1 value for different series, starting from Lyman N1 is equal to 1 to Fund where N1 is equal to 5. Right. Now, they will ask you questions like this. Okay, the question will be like, determine the shortest and the longest wavelength in Lyman series, something like that. Okay, they'll ask you, find the shortest and the longest wavelength in Lyman series or Passion series or whatever it is. Okay, now please understand, I'm going to give you a shortcut to find this out. Okay, so whenever they ask you about shortest wavelength, lambda minimum, that's the shortest wavelength, and that, remember that obviously depending on what is the series, N1 value will be same, right? But remember, I'm talking about the N2 value. N2 value will be infinity. Please remember this. Okay, if you want, you can mathematically check. Okay, the minimum lambda, I'm not talking about the wave number, guys. I'm talking about lambda. Whatever if lambda minimum, I'm going to have wave number maximum, energy maximum. They can ask the question in terms of energy also. Remember, energy and wavelength are inversely related. Okay, so if you want to find the minimum, the shortest wavelength, for that N2 value should be infinity. N1 value will depend on what kind of series it is, right? And if you want to find lambda maximum, you have to put N2 as N1 plus 1. Please remember these two. It is going to save a lot of time. Okay, right? So please remember that minimum wavelength would be, for minimum wavelength N2 should be infinity. For maximum wavelength N2 should be equal to N1 plus 1. Say for example, if it's Lyman series, lambda max for lambda max N2 should be 2. Okay, so this is what you have to understand. Okay, and one more thing what you have to know is another formula. This is gonna give me what is the maximum number of spectral lines right? What is the maximum number of spectral lines coming from, say, from some orbit to another orbit? Okay, right? So obviously I say that from n1 is equal to, from n is equal to 5, right? Obviously if I have to reach n1 is equal to, I mean n is equal to 1, how many such transitions are possible? So you can put directly 5 to 1, you can put 5 to 4, right? And then 4 to 3, like, so there are so many kinds of transitions possible, and I'm going to give you the direct formula to find out what is the maximum number of maximum number of spectral lines or transitions possible for that particular from the higher orbit to the lower orbit of 1. Obviously the lower orbit is always 1. Okay, now that would be n into n minus 1 divided by 2. Okay, this n is, for example, if it's from 5th orbit, you have to find put n value as 5. Okay, so if at all n is equal to 5, you can easily see n is 5, n minus 1 will be 4, 4 into 5 will be 20, 20 by 2 will be 10. So there are 10 possible ways by which you will be able to reach from n is equal to 5 to n is equal to 1. Okay, right? So that is one thing. Oh yeah, so yeah, that is about your Bohr's model, people. Okay, what is the time? 12:23. So there are obviously going to be limitations of Bohr's model. Let me complete with that. Okay, I'll tell you what are the limitations of Bohr's model. Okay, so first limitation is obviously it is going to work only for single electron species. Okay, it is going to work only for single electron species. Okay, right. Obviously single electron species like hydrogen, helium plus, Li2 plus. Okay, it is going to work only for these kind of species, right? If at all I have just lithium or boron, no, it is not going to help. It is not going to work. Bohr's theory. Okay, second thing is that Bohr considered only particle nature. Okay, Bohr considered only particle nature, but when de Broglie gave his hypothesis that we'll see in the next class, okay, in the evening class. So de Broglie said that the electrons can behave both as a particle as well as your wave, right? So again, a dual nature was a problem. He considered only your particle nature, but according to universally accepted truth is that any electromagnetic wave can have dual nature, right? Okay, next is about Zeeman effect and Stark effect. Right. So what happens is, so if I record a spectrum, right? If I record a spectrum, right? So what happens is, if this is the line which I'm going to get, okay. Now what Zeeman effect says is that it is the splitting of the spectral lines in the presence of magnetic field, right? So when I apply a magnetic field, right, these spectral lines are actually going to split into so many parts. Okay, now if this splitting happens in terms of I mean because of magnetic field, it's called Zeeman effect, and if it is going to happen in because of electric field, it's called Stark effect. And these two effects were not, like, these two effects where Bohr was not able to explain why is it happening. Okay, the spectral lines were splitting in the presence of magnetic field or electric field, and he was not able to explain why exactly is this happening. Okay, so these are all the different problems or limitations where for Bohr's atomic theory. Okay, so there are still more things. We are going to see the dual nature of light, not for electrons also, obviously. right? De Broglie's hypothesis, we are going to see one formula, and then we are going to see there are certain experiments to prove that light can behave as a particle. There are experiments to prove that light can behave as a wave. I think you would have studied the wave nature, ray optics and wave optics, right? So you have studied there. Obviously, in wave optics, you have studied interference, diffraction, and all these Young's double slit experiment, not split experiment, double slit experiment, right? So all these you have studied. That proves the wave nature. So we will see photoelectric effects. Okay, so photoelectric effect proves that it is going to have particle nature. Again, there are going to be some equations, and then we'll go on to see what is the quantum mechanical model, the last one. And obviously, in that, you will be seeing the quantum numbers, the most important part, and this chapter will be over. And after that, we'll be doing some problems. Okay, so guys, I know I just ran, right? But I know, like, assuming the fact that you will be knowing something in this chapter, that's why a little I just have to go a little fast. Is there any questions you want to ask? I can now ask.
Sir, how important are theory-based questions from this chapter, sir?
Yes, it is important. It is like whatever I told you, this much you remember, like this much you know, overall story, enough, more than enough.
Including the experiments and all, sir.
Experiments, I have seen questions coming in the sense that in terms of limitations of Bohr's theory, right? Theoretical question will not be tough and all. You don't have to worry about it. If you just know the logic behind it and the story, little story behind it, I think you'll be able to manage. But again, predominant questions will be only in the form of problems, and especially if you're going to get questions from atomic structure, 90% of times it is going to be from quantum numbers, not from what, like very rarely you will be getting questions from other areas.
Okay, sir.
Right. Cool. Fine, guys. I'll stop with this for now. Again, we have a class at 5 o'clock. We'll meet at that time. I think I'll be completing the chapter and we'll do some problems on everything, whatever we saw. Okay. Fine. Thank you so much. We'll meet again.
Thank you, sir.
Thank you, sir.
Thank you, sir.